Okay, so this one is interesting because there's a few ways you could do it, right? If I look at sine and I understand what sine looks like, sine is a function that goes from 0 to 1, kind of has this behavior. Or this is 1, this is -1. And so what does this remind you of? It might remind you of this problem where it's kind of a hidden way of writing that my series is alternating from -1 to 1. Okay, so that's our first hint. And so we might be thinking, let's do alternating series test. But the thing with alternating series test is that if you do alternating series test, then you have to verify that after you take away the part that makes it oscillate between 1 and -1, you have to check if this 1 over 1 plus 2 to the power of n is decreasing. And that's not extremely obvious because here we know that 2 to the power of n is growing super, super fast. And so we can likely see that the 2 to the power of n is making it decrease, but there's actually an easier way. And the reason why you might recognize it is because this 2 to the power of n should remind you of something that you've done before. It should remind you of the geometric series. So what does the geometric series say? It says that if you have n from 1 to infinity of r to the n, if r is less than 1, then actually the geometric series converges. And the basic idea is, well, if I have a 1 over 2, I keep on squaring it to the power of 3 to the power of 4, keep on adding it, it should get extremely small to the point that it will not add up to infinity, it will just plateau. And so that's what the geometric series is saying. So actually we want to do a few different steps. So I want to start off by doing the absolute convergence test. And what does this mean? Absolute convergence just means it's a really similar idea to alternating series test. It's the idea of taking away the negative part just by adding an absolute value. So I'm just going to define this as an, my series. This is an, so I want to take the absolute value of an and see how we can bound it. Because the idea of absolute convergence is, well, if I have an alternating sequence like this, if I add up all the terms, and the negative, yes, and the terms are alternating between positive and negative, and those converge, yes, for sure, my sequence will converge. But even a stronger statement is that instead, if I took the absolute value, which is just turning all of these negative values positive, if I turn all of these negative values positive and I add them up and I still get a converging series, then for sure my series will be convergent. Because that just takes away, because this bottom sum is for sure greater than this one, because this one involved me adding negatives. Okay, so that's the idea of absolute convergence. And so absolute convergence is only helpful sometimes. And the main reason I wanted to use it is because of this 2 to the power of n. So let's do absolute convergence. I'm going to take the absolute value of an. So I take the absolute value of sine a over an over 1 plus 2 to the power of n. Well, if I take the absolute value, it's basically like saying my sine negative stuff, instead of it looking like this, I just want to take the positive. So it will look something like this. But I also know this. if sine goes from -1 to 1, this will for sure be bounded by 1 over 1 plus 2n, because 1 is the largest sine will ever be. And then finally, I can do a limit comparison test. Because look, if I divide by more on the bottom, it's giving me a smaller piece. So I also know that if I divide by less, it will give me a bigger piece. So 1 over 2n for sure bounds this one. And it's really important to establish an upper bound, especially if we're trying to prove that something is convergent. Because if I say that this is larger and this converges, then this is smaller, then that one surely will converge as well. But look what we have. We have that 1 over 2n is has absolute convergence. And because of this, we know that 1 over 1 plus 2n has absolute convergence. And then furthermore, since this is larger, this will have absolute convergence. So a picture of what I just said. Let's assume that 1 over 2n has absolute convergence and it looks like this. By setting this as an upper bound, I'll say that this is always less. And then I set this as another upper bound and say that this is even less than this. And so it's kind of like we're squeezing all of this to converging. We're saying that if this converges and this is always greater, then definitely it bounds this one, and so this one will always converge. So that's the idea. So this is convergent by absolute convergent test and comparison test.